a few bits about the Science Gateways Community Institute, which is funded, let's see, we were funded in 2016 by the National Science Foundation to provide a variety of services and resources, and they fall into three main areas. The first area is support for building and running gateways. That includes developers who can give you hands-on support, creating a component or an aspect or even the whole beginning of your gateway. We have consultants who can also provide advice about specialized topics such as cybersecurity or usability and graphic design. We have also a catalog of gateways and software that can be used to build gateways. So the gateways that are listed are to highlight the gateways as something that can be used by any researcher or educator as appropriate. But the software collection, which is also quite substantial, nearly 100 items, I believe, is various components and platforms that you might want to use in constructing your gateway. So Galaxy today is one of those that is listed there. Also, through our education and training area, we offer this webinar series. We also offer Gateway Focus Week, which just last week we did a virtual mini version of this. And I'm sure that more will come. We have a variety of student-focused programs, and if you notice on the first slide, we are newly offering academic year internships. So if you have interest in including a student into your project as someone who can contribute to your code and such, we encourage you to look into applying that or encouraging students you know to apply for that, because we always need hosts. And then, of course, our website has lots of resources you can check out. And finally, our focus on networking and community, given that we have community in the name of our organization, is focused on a number of activities. One of these is our annual conference, which will be coming up in October. Our community forum is a Google group that you can join, and it is open for posting. So if you have questions or you have something you'd like to share, you can share it there. You can also email us if you want us to share it in our main newsletter. We're happy to do that, but that is a place where exchange is allowed back and forth. We have two programs that are called ambassadors programs. One is called the Science Ambassadors Program, and I'm just going to mention this, highlight this at the moment. Our Science Ambassadors Program actually is open for applications now through the end of June, and it provides up to $1,000 to support someone who wants to promote the use of a gateway to a disciplinary area. So you can either do that as presenting, say, at a virtual conference, given that most of them are virtual these days. You can offer training, and we also can provide money to support open access publishing. So I encourage you, if you know someone or if you yourself are interested in getting some support through that program, to have a look at our website and apply for that by June 30th, and then it will have rolling application acceptances they're onward, but basically until funds run out for the year. We also have the Gateway Ambassadors Program, which is more of a network of people who are on campuses who find themselves supporting gateways in various ways and want to connect with other people who serve that role. Our Affiliates Program, which also Galaxy is a member of, is a program that essentially allows software projects to indicate that they're willing to support a project that's interested in using that software, and they're just sort of highlighting the fact that they're available to be contacted. Our partner program also highlights other resources that are strategically useful and related to the kinds of services that we offer. And finally, we have news, blog, and job postings, and we always look for yours to include in that. So just to wrap up and hand off, I just want to remind you that we do put a evaluation up for, we have it available after every webinar, and we do use your feedback to shape the future of what we offer. And this series featuring gateway programs or platforms rather did come about because people were interested in hearing about a bunch of those. So your input is useful, and I'll post this in chat before the end of the webinar. So with that, I'm going to hand off to our speaker for the day. Nate Coraor is from the Galaxy project. And if you were lucky enough to join us last week, or last month rather, I should say, his colleague Dave Clements talked about how the Galaxy community has built itself and engaged people. This time we are focusing on the technology itself. So he is here to share that with you, and I'm looking forward to finding out more about Galaxy myself. So take it away, Nate.
All right, thank you very much, Catherine. So I'm going to be talking today about some of the more technical details about how Galaxy grew from a single server application into a sort of large distributed system that runs across multiple sites inside the US, and also the efforts that other people are doing elsewhere in the world to do some pretty exciting stuff with Galaxy. There is a link to the slides here on the title page if you want to follow along. All right, so the first question that I should probably answer is, what is Galaxy? And the answer to this really is best covered if you watch Dave Clements' talk from last month, his webinar, which is linked. However, if you didn't attend or haven't watched that yet and are not already familiar with Galaxy, I will cover it very quickly here. So Galaxy is, it's a platform for integrating command line tools and compute resources, and it's a UI for running those tools. So it allows users who don't have command line experience and are not used to working with software in that manner to get access to powerful bioinformatics tools that are run or that are made available. And it is free and open source software that anyone can download and use. So at the simplest level, Galaxy essentially turns this on the left side, which is what we call a tool configuration or a tool wrapper. It is the description of how to run a tool. And so you can see it defines certain things like, okay, this is the HiSat2 tool. It depends on some software packages, and we define things like what constitutes a successful run of this tool versus what constitutes failure, and then a template for how the command line will be generated when Galaxy actually runs this tool. So it turns that description that a tool developer writes on the left into a form on the right, which is what is presented to users in the Galaxy UI. And then when a user executes that tool, it becomes this command line that is then executed somewhere by Galaxy. And we'll get into the details on that somewhere eventually. So Galaxy runs on a variety of systems. It runs on your laptop. That's how we all do development in Galaxy. It runs on on-premises infrastructure, runs on HPC systems, both dedicated clusters, shared clusters, big supercomputers. It runs on private clouds, it runs on public clouds, or it can run on any hybrid of the above things. And for an example of that, we have usegalaxy.org, which is what I'm going to talk about at length today. So usegalaxy.org is a free public cloud service to perform genomic analysis. And we consider it a democratization of command line tools and complex HPC. So like I said, if you're a bench scientist who has no experience with running things on the command line, doesn't know how to submit jobs to the cluster, or in a very advanced way, we make that simple through the use of Galaxy. At usegalaxy.org, we provide everyone who registers with 250 gigs of storage, and you can get up to a terabyte for temporarily for single projects. And then we offer a varied amount of compute. And what I mean by varied amount, you'll see in a bit as we talk about all the different computing resources that usegalaxy.org provides access to. So a bit of the history of this service. So in 2006, we set up the first free public Galaxy servers. We called them test and main, one for Q&A, one for QA, quality assurance, and one for production use. And these ran at Penn State on a single server with something like 4 gigs of memory and 4 cores. I don't even remember anymore. 5 disks internal to the server. It's very small. But in 2006, we got some decommissioned cluster nodes from a cluster that my boss, Anton Nekrytenko at Penn State, had committed funds to build. So Galaxy's first cluster was made up of nodes that were maybe 5 years old and not in the best shape, but we got them, and that allowed us to grow. But one of the biggest changes, so we kept on adding hardware to Galaxy over time as we could get little pieces here and there. But the biggest shift came in 2013 when the Cyverse, the NSF Cyverse project, formerly iPlant, granted us some resources at TACC, at which point we renamed Galaxy Main to use galaxy.org and started running things out of Texas. So in 2015, then Galaxy received its first allocation from XSEDE. XSEDE is the big NSF project to unify or provide resources across large supercomputing centers in the US and grant them to researchers through a granting process. So that brings us to 2020, where usegalaxy.org now distributes jobs from TACC to a dedicated cluster at TACC that we've been using since 2013. Stampede-2, the supercomputer there, Bridges, a large memory supercomputer at PSC, and then Jetstream, which is an OpenStack-based cloud divided into 2 zones between IU and TACC. So we'll talk about how we make all of that happen. And I'm going to use sort of a leitmotif here throughout the talk of how growing and expanding onto these resources was a series of challenges and the solutions that we came up with for those challenges. So one of our earliest challenges, as I mentioned, was in 2013, relocating Main from Penn State to TACC. And by that point, we had amassed hundreds of terabytes of data. So it started on that single server, but over time, we added multiple storage servers. Because one of our philosophies from very early on is that Galaxy data is always created, and we never allow you to modify it directly. So you can always go back and view the old results of your analysis. You're always building off of those. So users can delete their own data, but for the most part, we're never deleting a user's data without their consent. So by this point, we had hundreds of terabytes of data, and we wanted to move the whole site over to TACC with a minimal amount of downtime. And the solution that we came up with at that time was to create the hierarchical object store Galaxy plugin. And so I need to take a diversion here to define some stuff. So object store in the Galaxy language is the application layer in Galaxy that abstracts access to stored data. So in old versions of Galaxy, whenever it needed to open and read a file, it would just do it wherever in the code it needed to be done, assume that that file is local to the Galaxy server, open it up, read it, do whatever. But in 2011, my colleague NSF-funded created this object store layer that made it so that all calls to open, read, close, write data all went through this access layer, and it was pluggable from the beginning. And in the beginning, we supported essentially a disk storage option. So it still had to be a file system that's mounted to the Galaxy server, either a local disk or NFS or whatever. It has to appear as a mounted file system on the Galaxy server. But this opened up a whole lot of additional options for us. And one of the first things that we did then was to create a distributed object store meta backend, because we were growing Galaxy very piecemeal at the time. It sort of always has been that way. And we didn't have a fancy scale out storage system that would allow us to add new disk and grow the file system and have it all appear as one big logical file system. So we had, before we moved to TACC, Galaxy was spread across, the data was spread across 6 different servers, and the distributed object store is what allowed that to happen. So you would create a list of all these file systems where Galaxy can store data. You could weight each one, and then Galaxy would choose when it creates a data set, I'm going to put it in, one of these backends based on the weight of that backend. And then in 2013, we moved to TACC. My colleague Dan and Baker created the hierarchical object store, which is similar to distributed, but it did not require that you knew where the data was before accessing it. And I'll explain that very sort of confusing concept with a picture. So what we had was the ability to mount our file systems from Penn State and the big new file system that we were going to use at TACC, which is Coraor there on the top right, all up on the same Galaxy server at TACC. And then what existed inside this distributed backend bubble here was how things were at Penn State. So we could access things from these different pools. But then using the hierarchical backend, we were able to write new data into the new file system at TACC while still reading from the ones at Penn State. So it would, if you wanted to read a data set, so data set 1, for example, it would check, okay, is this available in backend 0, which is the one at TACC? No, okay, try backend 1. It says, yes, it exists. It's in pool 2. I know where to find that. And the data would be returned to Galaxy. But any new data that was created would go into the new backend at TACC. And that allowed us to transfer all of the existing hundreds of terabytes of data out of band to TACC. And as soon as it had appeared there, once it had been copied over, it was immediately available for use at TACC without any interruption to the user. So through this, we ended up moving the server, I think 2 months before all of the data was finally moved over to TACC, but nobody really noticed. Another thing that happened around that time is that the cluster that we were submitting jobs to at Penn State was using Torque PBS, whereas the new cluster we were going to be running at TACC ran Slurm. And we didn't have any experience with Slurm at this time, but we had made some decisions early on in the development of Galaxy that made this quite a bit simpler. So in 2006, when we added support for Torque, that was made pluggable. So at the time, there were only 2 plugins, essentially. One was to run jobs locally on the Galaxy server, and the other was to submit to Torque. But in 2010, we then added a plugin for this Drama, which is the Distributed Resource Manager Application API, something like that. And it's essentially a common API translation layer between a cluster scheduler's proprietary API, such as the one that comes with Grid Engine or Slurm, to a common one. So we added this in 2010 because some people in the community wanted to run jobs on Grid Engine. We didn't run Grid Engine ourselves, but we had made this pluggable job system, so we added a plugin for this Drama. And in 2013, that paid off for us as well, because we were able to just use Slurm pretty much out of the box using this Drama plugin that we had already developed with just a small amount of additional work. So another challenge that came along early in the development was a need to install tool dependencies automatically. And so I'll go back to the dictionary here, the Galaxy dictionary. A tool dependency in Galaxy language is the underlying software that's needed in order to execute a given Galaxy tool. So if you recall the XML that I showed you much earlier, that was the HiSat2 tool, but we, the Galaxy developers and community, generally don't write the underlying software that we provide in Galaxy. That's stuff that other people do, and then we just wrap it into Galaxy. But that means that we needed a way to actually install all of that software so that Galaxy could use it. And originally, when Galaxy was running at Penn State, I would just install this all by hand into a big file system and use GNU Stow to manage versions and that kind of stuff, and make it so it was all available on the path so that Galaxy could find it. But that was not a very sustainable solution, not for me personally running that server, but not for the community of people who want to run Galaxy servers as well. So these tool dependencies, just to highlight how big this problem can be, these tool dependencies can be any command line executable, from grep to specific versions of Python to very specialized domain-specific tools like HiSat2. And the versions matter even for simple tools like grep. So if you have a new version of grep that comes out, it may have a new flag that gets added. And if the person who's wrapping that tool in a Galaxy uses that flag, but then where that tool gets run is using an older version of grep that doesn't have a flag, the tool is going to fail. The same thing goes for things like a lot of people develop Galaxy tools on Mac OS, and the version of grep that you'll find in the command line there is the BSD version, has completely different options than the GNU version. And so the same thing is true. If you develop that tool for the BSD version of grep, it may not work at all with the GNU version. So there's a multi-part solution to this problem of tool dependencies. One you've seen already in the XML, so we added this ability for tools to define their dependencies. Say, I need this software package having this name with this exact version. And then we added a dependency resolver to Galaxy so that if that package with the name and the specific version could be found, then it would be used by Galaxy. And then part two of this process was to create somewhere to actually provide this software from. And that's the Galaxy Toolshed, or Galaxy version of an app store, written by my colleague Greg von Kuster. And it housed recipes for downloading and compiling binaries. We created the Toolshed way back in 2010, 2011, and at the time there were no real good alternatives for doing package management. Most package management was considered at the operating system level or Linux distribution level, and there was no real good way to do this. And what Greg built in the Toolshed worked reasonably well after it matured, and this was the system we used for quite a while. So that was sort of the state of things in 2013. Now, today in 2020, usegalaxy.org is a pretty large distributed system. And this is a fun graphic that I usually throw up at the end of my talks to say, I don't expect you to trace out all these lines and really figure out what any of this means, but it is a cool way to visualize how much can be done with Galaxy and the ecosystem that we've created with it. But we have more time today, so I can take that and say let's take this picture apart and see how the pieces actually fit together and how it works.
Before you get started with that, we just got a question in from Mona.
Mm-hmm.
She said, if a software that's depended on by a tool isn't available, how does the system handle that?
So there is the dependency resolution system is pluggable, just like so many other things in Galaxy, and you configure those plugins. So it will search through each of the things that you've defined, and if it can't find it, it will just try to execute the command anyway. And if it's on the path, then it might succeed if it's the right version. If it's not on the path, then it's going to fail. So
I guess, well, the question would be additionally, like, if it just isn't there at all, like, how do you know, or does it tell you if like that software doesn't exist?
Yeah, you don't. Well, there's a management panel in Galaxy that shows you whether or not the resolver, the dependency resolver in Galaxy, thinks it exists. If the
Mm-hmm.
tool is installed, then a user can run it, and if it's not installed, they're going to get an error message.
Terrific. Okay. Yep. She said that's good. Thank you.
Great. Good question. So just looking at the parts of this that are sort of the 2013 version of Galaxy, these are the components that we need to run a robust Galaxy service. And if you run your own Galaxy server that interfaces with a single cluster and has network mounted storage, it probably looks a lot like this, except as far as I know, we're the only, or one of the only sites that runs multiple VMs to run Galaxy services. And most people run it in a single VM, which is more than enough in most cases. So we have 2 VMs for handling web requests, 2 for handling Galaxy jobs, so the process of preparing a job to run, submitting it to the cluster, monitoring its state, finishing it up, collecting outputs, that sort of stuff. We have 1 VM for the database, 1 for the Slurm controller, and then we have our bare metal cluster. All of these things mount a common NFS mounted file system that's run by folks at TACC. So digging actually down into those VMs and seeing how the Galaxy server is constructed, we'll take a look at, so if you've got the Galaxy website, usegalaxy.org up in your web browser, what you're seeing is a web connection to Nginx. That's going to proxy the Galaxy web application, which is actually running inside of the UWSGI application server. This gets us some nice features like load balancing across multiple processes, restarts that don't, uninterrupted restarts so that they don't affect users, that sort of stuff. So we have 2 of those web serving VMs, and then we have 2 job handling VMs, each of which runs multiple Galaxy job processes or servers. So these are essentially the same application as the web. I mean, it's the same code. It's just run without UWSGI. It's started directly with Python because we don't need any of the web serving functionality for these processes. These communicate via a Postgres database. So almost everything you see in Galaxy that's persisted is stored in a Postgres database, with the exception of the data itself. So all of the user data is files on disk or in an object store or something. But everything else about it, the user information, the representation of your history, all these things in Galaxy are stored in a database. And then you have a cluster node, and in our case, there's 16 of them. And these are all mounting the same shared file system. So one of our next challenges then, once we had everything running at TACC, in a data center at TACC, was to run the Trinity genome assembler on Blacklight, which was a big, large shared memory system now decommissioned at PSC. So genome assembly takes enormous amounts of memory. And so this was a great resource. This is something that we had no ability to do in Galaxy prior to the use of the availability of Blacklight. So this presented one of the biggest challenges for Galaxy, in that when you run Galaxy jobs on a local cluster, you have this shared file system. But when you run it on a remote compute resource, or when you want to run jobs on some remote compute resource, you don't have access to the same file systems. So Blacklight in this case has its own cluster file system, but that's not available to the Galaxy server. So what do we do to get these jobs running over there? And our solution was a piece of software that we call Pulsar. So it was developed by my colleague John Chilton for Galaxy, and it runs as a service on a remote login node, the login node of a remote computing resource, so Blacklight in this case. And it communicates via AMQP, the messaging protocol. It stages data over standard web requests that are initiated from Pulsar to Galaxy. So it's very firewall friendly. We generally don't have issues with cluster admins, HPC system admins with running Pulsar there, because it doesn't need a port, it doesn't listen. All of its connections are created outbound. And then Pulsar handles staging the data to and from the remote system. It manipulates the paths so that the fact that the file system where the data lives is not the same is corrected. And then it resolves the dependencies on that remote resource and generates a command line, does all the interaction with the cluster scheduler over there, and then sends the outputs back to Galaxy once it's done.
A quick interrupting question. Junhan asked, he said he was aware Galaxy was using Python 2.7, and he's wondering if now Python 3 is supported.
Yes, from largely a community-driven effort. We have a wonderful community in Galaxy, which Dave talked about, and I'll talk about some more, but it is now Python 3.6 and newer. Now supports it, and support for 2.7 is officially dropped.
Oh, okay, great. Thank you.
So Pulsar sets up and runs jobs on that remote system, and it can use dependencies from the remote system, but it can't install them if they're missing. So in this trial run where we used Blacklight, is there another question? Sorry.
Nope, no other question. I was just responding.
Gotcha.
Yep.
So in this sort of first run, we used Trinity, and there was actually a special version of Trinity that had been modified by folks at PSC so that it would run most efficiently on Blacklight. And that was installed using the module system, if you're familiar, on HPC systems. Most of them use it. And Galaxy's dependency resolver because it was pluggable, had this ability to use modules. And Pulsar was adapted to use the same dependency resolution system as Galaxy, so it gained this ability as well. So it was able to use the version of Trinity that was installed over in Blacklight, but that's because it was already installed. So additional resources available to us via XSEDE opened up a ton more computational potential, and Pulsar made it possible to use this. So like I said, Blacklight was sort of our first attempt at this, but we wanted to run more. So we had eventually access to run jobs on Bridges, which was the successor system to Blacklight, and Stampede 2, the former number 5 or 7, whatever it was, top 500 supercomputer in the world at TACC. And we wanted to be able to run more than just a single tool. We started out doing this by sort of manually copying and installing dependencies the way that I did in Galaxy before we had the toolshed system for managing dependencies, but that wasn't going to scale. Other people who wanted to use Pulsar couldn't do the same thing or had to do it themselves. So, and you couldn't use the toolshed installed dependencies with Pulsar because they were tightly coupled with Galaxy and not with Pulsar. And we could have updated Pulsar to do this, but by this point, something else had come along that made this all much easier, and that was Conda. So Conda is a cross-platform, no privileges required package manager. That means that you don't have to have root access to install and use packages from Conda. But one of the key features that we really needed is strict version management and isolation. So when you install packages from Conda, you can say, I want this exact version of this package, this software, and I want it installed into its own isolated environment where it doesn't affect other packages that I've installed from Conda. And because each version of a Galaxy tool depends on a specific package and specific versions of those packages, this was perfect for us. And BioConda is an effort by a number of community members to package bioinformatics software for Conda. If you've ever worked with bioinformatics software or really domain-specific scientific software in general, you know that it's generally, you're lucky if it's, the source is tossed up on a website somewhere that you have to untar and try and figure out how it builds, and everything uses a different build system if it uses one at all. And it's just a mess. But thankfully, a lot of hard work from people in the community put this together to make, and then we were able to leverage that to use it. So Galaxy's support for Conda matured in 2015, and Pulsar later integrated that same support. So Pulsar was able to automatically install dependencies from Conda. So Galaxy would say, hey, I have a HiSat2 job to run, send it over to Stampede2. And if that version of HiSat2 wasn't installed, then it would be automatically installed by Pulsar via Conda, and the tool should just work then. So this was a huge leap forward for us being able to run more than just a specific one or two tools.
I don't know if this is a good point to ask you a couple brief questions.
Sure.
That came in just as you started the section. One question was whether, from Chunan, whether Galaxy Pulsar supports non-root privileged environments?
Yes. It supports both, but certainly, I mean, I don't have root privileges on Bridges or Stampede or any of these things.
Okay, and then the other question was from Mona, can Pulsar handle large multiple terabyte size data transfer well?
So it's using curl, libcurl, to do the transfers, which does support resuming. So if the transfer is interrupted, it can be resumed. I don't know that I've seen it with data sets that large, simply because our quotas on usegalaxy.org generally prevent anyone from having a single data set that large. So hopefully yes, but I don't have any proof.
Okay, great, thank you.
Mm-hmm. So this system, this piece of the system where we're running jobs outside of the data center looks like this. We've got Stampede2 on the right, Bridges on the top, our two job handler VMs as before. And you'll notice via the green lines, these are the only things that have the NFS mount to the place where our 3.5 petabytes of user data is stored. All of that transfer then, when data sets have to be sent for job inputs and collected back as job outputs, happens over this HTTP connection between Pulsar and Galaxy. And then there's a message queue, RabbitMQ, that does the control messaging. One nice bonus that we got out of Conda and BioConda is that there is now a biocontainers project, which takes the environments of tool dependencies and software packages installed via BioConda and Conda, and turns them into Docker and Singularity images that are then hosted. And this gives the highest possible level of reproducibility using current technologies, because if I install HiSat2 from Conda today, even if I specify a specific version, that environment that gets installed to may not be the exact same one as if I installed it a month ago. And that's because all of HiSat2's dependencies are installed pretty much unversioned, unless there's some kind of specific pinning. And that can cause problems. But with biocontainers, you're getting an exact image of that software package and all of the dependencies as installed at that time. So you are running the same software as anyone else using that same biocontainer. Okay, so next challenge that we had then after we had these jobs running on these big HPC systems was that the NSF funded the Jetstream cloud. It's an OpenStack-based cloud divided into 2 zones at IU and TACC. And this is a much different mode of operation from HPC systems that we've been running on so far, because we have to manage cloud instances. We have to set them up the way that we want them. So, but we have a lot more flexibility because these are our own systems. We have root, essentially, on any cloud instances that we start. And we want to be able to run now, instead of just a curated set of tools, any tool that you can run in Galaxy. But a lot of these tools have some additional dependencies or needs. So, of course, they have their tool dependencies that we've already discussed. We have 8 terabytes and growing of reference data that many tools make use of, and the Galaxy source code itself, which I didn't mention this earlier, but we have I have to maintain at a specific version, the same as the one that's running on the Galaxy site at each of those HPC systems. For 1 or 2, that's not a big deal, but when we're starting up potentially hundreds of cloud instances that all have to have that same version, it becomes much more difficult. So our solution to that problem was to store all of this stuff in the CernVM file system. And just a quick primer on CVMFS. It's a read-only web-based file system that was designed for software distribution, but we use it for software and reference data. It's geographically distributed and fault tolerant, so there's a canonical copy of a repository or a file system, they call them repositories, on what's called a Stratum 0 server, and then this is mirrored to any number of Stratum 1s, and then through any number of intermediate proxy servers if you want them to do caching. Clients then mount this file system and see it as if it's local, but they don't actually pull any data from the Stratum 1 servers or elsewhere until it's accessed. So you don't have to have a full copy of this data anywhere other than dedicated servers. So we've built up a network of CVMFS servers. The ones that I originally set up were at Penn State in Indiana and at TACC. And then this became useful for other people in the community. So the folks in Freiburg at Galaxy Europe set up a server. The EU set one up in Italy, and the folks with Galaxy Australia set one up in Melbourne. So the piece of our big diagram that shows this CVMFS deployment looks like this. You have the Stratum 0, 2 Stratum 0 servers, one at Penn State, one at TACC, and then copies of the data on those servers are mirrored to Stratum 1 servers, which I run actually 2 of them in Jetstream itself. One at IU, one at TACC, and then a 3rd one at Penn State that's just generally available. You can see that the solid line is the connection between the client. So when it mounts a file system, it accesses it from a Stratum 1 server. And then there is a failover, or rather the dashed lines are copies from the Stratum 0 server to the Stratum 1. But then there's all these dotted lines that come in, and these are failover connections. So the preferred method is that a node running in a given OpenStack zone is going to access the Stratum 1 that's local, because that's going to be fastest. But if that Stratum 1 goes down, as occasionally happens, the nodes don't have to just start failing. They can fail over to any of the other Stratum 1s that are available. But there's a piece missing in this picture. So we have the way that we can get access to all this data that we need, read-only data, but we need something to manage the nodes. So you can see I like they gray out, that each node grays out more as you go down, and that's to represent the idea that these are scalable instances. And the reason for that is that XSEDE charges our Jetstream allocation using the amount of time that that instance is running on Jetstream times the number of cores that it uses. So in order to not burn through our allocation, we don't want to keep a bunch of instances running that we're not using. We want them killed off and start them on demand. So how do we manage this cluster of OpenStack instances? It turns out that Slurm, our favorite cluster scheduler, has some support for this built in. So originally we did sort of manual scaling of these instances, but eventually this support got better. Slurm tells us when and what nodes should be started, but it doesn't tell you how to do that. It has no understanding of cluster systems or cloud systems of OpenStack, any of these things. So we do that. We provision and configure and start stop things using Ansible whenever Slurm tells us. So when you combine the Slurm and Ansible, you have what we call Galaxy Slurm Scale. And if you've never seen Ansible before, well, if you're not familiar with what Ansible is, it's a deployment configuration management system. It's a essentially YAML-based declarative language for how tasks should be performed. So in this case, we say we either want to start a new instance on Jetstream, or if that instance already exists but it's stopped, we want to power it on. Wait for it to become accessible. If it's a brand new instance, we don't maintain images in OpenStack. That's kind of a headache if you can avoid it. So if it's a brand new instance, the first time it's being run, we run through a bunch of setup tasks. We install CVMFS, we install Slurm, and so forth. And then we say, okay, Slurm, here's your new node is available, has this IP address. So Slurm essentially tells us when we need new nodes, and then this process gets run through Ansible to do it. And then the same is done to stop them. Slurm tells us when to stop. There's a little Ansible that runs to shut them down. So that was our solution for that scaling problem. When it's all put together in the diagram here, then we've added these new sections. We have a Slurm controller running in each OpenStack zone. We have our Pulsar server and an NFS, a volume that's mounted to this controller node that we run in each zone, which then provides data set storage local to that, but they get staged in and out via Pulsar. And then Slurm is connected back to the Slurm controller that we run at TACC via the multi-cluster functionality in Slurm, which allows us to make decisions about where to send a given job when it comes in. Oh, is there capacity available on Jetstream at IU or TACC or whatever? That's how we make those decisions. Was there a question?
There is 2 questions that came up. Mona asked, how is CVMFS performance, and particularly for lots of files or large amounts of data?
Mm-hmm. So it breaks the file catalog up into multiple pieces, which makes access relatively simple. From there, I think the performance is mostly dependent on a number of features, like you can set the cache size of the client, and then you have to consider where the cache is being stored on the client, a remote file system, or is it local, or that sort of thing. And then your connection to the Stratum 1 servers. So far, it's served us relatively well. If we were doing heavy access out of it, that might not be the case, but we haven't needed that so far.
Cool. And then the second question is from Chunhan. He asks, how do you manage identity and access between different clusters? Like in the sense of security, like cybersecurity type things like that, right? I think.
Yeah, okay. Mm-hmm. So the Pulsar communication between Galaxy and Rabbit and MQ and so forth is secured via SSL, essentially. And then there's a key that a shared key, a pre-shared key essentially between these that allows them to communicate. When jobs run then on the individual instances in OpenStack, they're just all running under our community account. There's just one account there. So we don't have to do any kind of special per user authentication
Okay.
on the OpenStack level.
Terrific, that makes sense. Okay, thank you.
Mm-hmm. All right, so finally putting all that back together, here's all the pieces. This is the same diagram I showed you close to the top. There's some additional stuff here for Docker Swarm, which I'm not going to talk about because we're moving away from it, and it's only used for one very specific small thing. But otherwise, I've pretty much covered this whole diagram for the first time ever, I think. So just a bit more about Ansible since I brought it up. So I started using it in 2013 for my own purposes, but over time, it became more popular. Other people started using Ansible and they said, hey, you're managing Galaxy with Ansible. I want to do the same thing. Can I leverage the stuff that you've done to manage my own Galaxy? And this turned into a nice little ecosystem that we've developed. So this is Ansible Galaxy, poor name choice by them. We had it first, but anyway, this is essentially their app store, toolshed, whatever you want to call it, for reusable components of Ansible called roles. And we've taken all the work that we've done in Ansible over the years and tried to publish it so that it's usable for other people in Ansible Galaxy. To the point that we're now, so we teach an annual admin training, a week-long workshop, and that's now done entirely using Ansible because we can do so much with it. And all of these pieces are available to build a really awesome production Galaxy server using Ansible. So that's the work of me and others. For example, all the CloudMan stuff that you see there was built by others who were part of the Galaxy project. And then even others, like for example, Galaxy Europe team is now publishing roles, and now I use their roles. I use their CertBot role, the GXadmin role. It's really turned into a wonderful thing that's supporting in many directions. And so that leads me to what has made Galaxy successful. I think one of the key things is that we had a good modular design early on that allowed us to very quickly adopt new technologies later. So one example was how we added that support for Grid Engine. And we had made that job system pluggable early on, and that made it very easy to support Slurm. And in fact, we support even more, LSF and PBS Pro and all kinds of stuff because of the way that we designed that system. In addition, the way that the object store was designed has allowed us to, now we're doing a trial run of storing data on our test server in iRods instead of directly on a file system. And this is going to allow us to do some pretty cool stuff, hopefully transferring directly between Pulsar and iRods instead of through Galaxy. And that was again possible because of the modular design that we used in the object store layer. And then our community is wonderful. Again, I encourage you to look at last month's SGCI webinar, where Dave Clements talked at length about all of the wonderful things that our community has done. But one thing that he sort of didn't cover is that we and members of our community are also involved in many other communities. And this has been amazing, right? So we've contributed back to Slurm, to Ansible, not just the roles, the public roles that we publish, but to the Ansible software itself to improve it. The Python Packaging Authority, Bioconda is pretty much led by a number of Galaxy community members, and as well as the Biocontainers project. And by fostering the community around these other open source projects, I benefit as the admin of usegalaxy.org, but lots of other people benefit, and Galaxy benefits as a whole. So yeah, that's huge. The community also is doing amazing things with Galaxy beyond what I'm doing. So this is a slide from Gianmaro Kukuru, who gave a webinar last month and talking about the Pulsar network that has been, that he's created between a number of sites in the EU as well as Australia. And so if you submit a job to usegalaxy.eu, that job may run at the cluster in Freiburg where it's based, but it also could run at any of these additional sites, all using Pulsar. Additionally, the Galaxy Australia and Melbourne informatics team, in collaboration with the Taylor Lab at Johns Hopkins, have put a lot of work into developing a Kubernetes-based Galaxy platform that usegalaxy.org is going to slowly be adopting over time. And this includes a Galaxy Helm chart. If you're not familiar with Helm, it's sort of an orchestration system for Kubernetes. And now there's a production Galaxy service that you can run that is entirely Kubernetes based. And this leverages the Genomics Virtual Lab, a project that grew out of Galaxy Australia with some more recent efforts by the Taylor Lab. And this is essentially a cloud-based image that can now run across, I think, 4 different clouds. It's very cloud agnostic, that can run lots of different environments, including Galaxy. So just really amazing stuff that's now possible. And this is incredibly easy to use. You go to the Galaxy Cloud Launch page, put in some credentials, and it starts up instances of Galaxy that are then immediately available for your use. And this leverages even work that we've done before, like our reference data. It's in CVMFS. It has access to all of that. So really, building these pieces and making them reusable for everyone has paid off. And finally, the Galaxy Europe team and Helena Rashi have created a automated infrastructure that is controlled by Jenkins. So when they want to change their Galaxy infrastructure, it's done entirely through pull requests on this repository, where Terraform then uses interfaces with OpenStack to make the architecture conform to the definition files that are written in this repository. So there's very little manual intervention into setting up and running architecture for Galaxy, which is a really beautiful thing. I wish mine was as fancy as this. So with that, I have a slide that I stole from Dave Clements last month. Thank you to the Galaxy community, Catherine and Naidi for the facilitating this call at this webinar, SGCI and our funding agencies, and thank you all for listening.
And thank you, Nate. That was great. I'm gonna steal the screen away from you. I know we're just past the hour, but I want to just let people know also about next month's webinar, which is more good stuff also about platforms. But in the meantime, I also have a question for you to answer. Mona had asked a question about she said, the whole system looks quite complicated. I'm curious how many people are on the Use Galaxy project. And I wasn't sure whether she meant by developers or in the community more broadly. I know it's huge, so I thought I'd throw that out there to you anyway.
So it's yeah, and Dave actually went into really good answer for this in his webinar last month, because it's getting very difficult to even define what the Galaxy team is. We used to use that term and we don't anymore, because there are now, I think, 5 or 6 people who have commit access to the Galaxy code that are not people that were paid by, you know, the main PIs that are part of the Galaxy grant. There are, yeah, so out of those 4 PIs, I think there's, you know, 30 or so folks employed to work on Galaxy, 20 to 30. But the community is much bigger, and Galaxy is much more the community than it is just the people working for the 4 PIs at this point.
Fantastic. Yeah, that I think that it covers it. She was curious about the developer and admin and marketing aspect. So it sounds like it's about 30, and then, but you leverage the activity of so many more people, it sounds like. So yeah. Fantastic. Well, thank you so much. You know, I don't understand most of the technology, but that was really clear for even someone who's not a technology person. So I appreciate.
I'm happy to hear that.
Yeah. I appreciate you making it so clear that even someone like me can piece it together and follow along. So thank you for taking the time, and also for being willing to reschedule on short notice.